For 100 years, we have told the same story. Look at distant galaxies, measure their light, see it stretch toward red, conclude they are moving away from us, conclude space itself is expanding, conclude the universe began in a hot, dense state and has been stretching ever since. It became one of the pillars of modern cosmology. The universe is expanding. But what if that sentence hides a misunderstanding? Not that galaxies are not receding, not that redshift is imaginary, not that the data is fake, but that our interpretation, the picture we built in our heads, might be fundamentally wrong. Because the moment you ask what expansion actually means, the story starts to unravel. Let's begin with something simple. When you hear the universe is expanding, what do you imagine? Most people picture an explosion, matter flying outward into empty space, like shrapnel from a cosmic bomb. That image is wrong. There is no center, no edge, no outside space into which the universe expands. Instead, we are told something stranger. Space itself is stretching. Galaxies are not moving through space away from a central point. The fabric of space between them is growing. It is a subtle distinction, and it might be where the mistake begins. To understand why, we need to revisit the evidence. In the 1920s, Edwin Hubble observed that distant galaxies are redshifted. Their light is stretched to longer wavelengths. The farther away the galaxy, the greater the redshift. This relationship, now called Hubble's law, was interpreted as evidence that galaxies are receding from us and from each other at speeds proportional to their distance. The simplest explanation: the universe is expanding. Einstein's general relativity had already predicted that a static universe would be unstable. Space could expand or contract. When Hubble's observations arrived, they seemed to confirm expansion. But here is the first uncomfortable question. Does redshift necessarily mean expansion? Redshift simply means that light's wavelength has increased. There are multiple ways this can happen. One is Doppler redshift, motion through space. If a galaxy moves away, its light stretches. Another is gravitational redshift, light losing energy climbing out of a gravitational field. And then there is cosmological redshift, where the stretching of space itself increases wavelength. The standard model assumes the third explanation. But notice something subtle. We never observe space stretching directly. We observe light. We measure wavelengths. We interpret. The idea of expanding space is a model. An extraordinarily successful one, but still a model. Now let's dig deeper. In general relativity, space-time geometry is described by a metric. The Friedmann-Lemaitre-Robertson-Walker metric assumes homogeneity and isotropy. Plugging this into Einstein's equations produces solutions where the scale factor changes over time. That scale factor is what we call expansion. But the scale factor is coordinate dependent. This is not a conspiracy. It is mathematics. You can choose coordinates in general relativity. You can describe the same physical situation in different ways. And here's where things get strange. In certain coordinate systems, galaxies appear to move through static space. In others, space itself expands while galaxies remain at rest. Both descriptions are mathematically valid, so which one is real? If the physics is invariant, if observables remain the same, then perhaps the statement space itself is expanding is not a physical fact, but a convenient interpretation. That sounds trivial. It isn't. Because if expansion is partly a coordinate effect, then what exactly is expanding? Are atoms expanding? No. Are solar systems expanding? No. Are galaxies expanding? No. Gravitationally bound systems resist expansion. Even clusters of galaxies do not expand internally. Expansion only manifests on very large scales where gravity is weak, which raises a deeply unsettling possibility. Maybe nothing is expanding locally. Maybe what we call expansion is simply how we describe increasing distances between unbound objects in a particular coordinate frame. Let's push further. Imagine you are standing in a vast, empty grid. The grid lines are fixed. Now imagine distant objects drifting apart due to initial velocities set long ago. From one perspective, you say, the objects are moving. From another, you stretch the grid and say, space is expanding. Both produce the same observable separations. Which interpretation is fundamental? Here is where the so-called massive mistake might lie. We reified the coordinate choice. We turned a mathematical description into a physical substance. We began talking about space as if it were rubber, stretching, pulling galaxies apart. But general relativity does not require space to be a material fabric. It describes geometry. Distances between world lines increase. That is the invariant statement. Whether you call that expanding space or moving galaxies depends on coordinates. Now you might object, but what about the cosmic microwave background? What about the uniform radiation bath at 2.7 Kelvin, interpreted as relic light from a hot early universe? Doesn't that prove expansion? It proves that the universe was once hotter and denser. It proves that photons have been redshifted. It does not uniquely prove that space is a physical substance stretching. In fact, some alternative cosmological models reinterpret redshift differently. Tired light models once attempted to explain redshift as photon energy loss over distance. Most were ruled out because they failed to reproduce time dilation and supernova light curves. But the point remains. Redshift is data, expansion is interpretation, and interpretations can evolve. There is another layer to this: dark energy. In the late 1990s, observations of distant type Ia supernovae revealed something shocking. The expansion of the universe appears to be accelerating. To explain this, cosmologists introduce dark energy, a mysterious component comprising roughly 70% of the universe's energy budget. Dark energy is not directly detected. It is inferred from the dynamics of expansion. But if our conceptual picture of expansion is incomplete or partially coordinate-based, then perhaps dark energy is also a symptom of misinterpretation. This is not a claim that dark energy does not exist. It is a reminder that cosmology rests on a framework, and frameworks can hide assumptions. Let's go even deeper. In certain formulations of general relativity, one can describe cosmology in conformal coordinates where light rays behave as if in flat spacetime, and expansion manifests differently. In other words, you can mathematically transform away the intuitive picture of space stretching and replace it with particles moving in a curved geometry. The observable predictions remain. The narrative changes. If two descriptions predict identical observables, then neither is uniquely real. They are different lenses on the same underlying structure. So when we say the universe is expanding, what we might really mean is the metric describing distances between comoving world lines evolves over time. That is precise, but it is not the rubber sheet cartoon. And perhaps our massive mistake was turning the cartoon into ontology. We began imagining galaxies being dragged apart by stretching space, as if space were exerting a force. But in general relativity, there is no force of expansion. Galaxies follow geodesics, natural paths in curved spacetime. Their increasing separation emerges from geometry, not from a pushing substance. That subtlety matters because it reframes the story from dynamic stretching to geometric structure. Now let's address a dangerous misunderstanding. Are we claiming the universe is not expanding in any sense? No. Distances between distant galaxies increase over time in our standard cosmological model. That is well supported by data. But the statement, space itself is expanding like a balloon, may be a pedagogical metaphor that hardened into dogma. There is another more radical idea gaining traction among some theorists. Perhaps what we interpret as expansion is a manifestation of deeper quantum gravitational degrees of freedom. Some emergent gravity models suggest space-time geometry arises from entanglement patterns. In these approaches, cosmic expansion could reflect changing information structure rather than physical stretching. If space-time is emergent, then expansion may not be a fundamental process at all. It may be an effective description of deeper microscopic dynamics. Think of temperature. Temperature is real. It predicts behavior, but fundamentally, it is statistical motion of particles. Perhaps expansion is like temperature, a macroscopic emergent phenomenon, not a literal stretching fabric. And then there is the Hubble tension. Different methods of measuring the expansion rate of the universe yield slightly different values. Early universe measurements based on the CMB suggest one rate. Late universe measurements based on supernovae suggest another. The discrepancy is small, but statistically significant. It may signal new physics, or it may signal hidden assumptions in our cosmological model. Either way, it reminds us that even our most confident statements about expansion are not final. Let's step back. What do we actually observe? We observe redshift distance relationships. We observe cosmic background radiation. We observe large-scale structure formation. We fit these to models derived from general relativity. The best fit model describes a universe whose scale factor grows with time. That is a triumph of physics. But the metaphysical interpretation, that space is a physical thing stretching like dough, may be oversimplified. The real picture is more abstract. Space-time geometry evolves. Distances between free-falling world lines change. Nothing is tearing atoms apart. Nothing is pulling solar systems apart. Local physics remains stable. The expansion lives in the geometry of large-scale structure. And geometry is not a substance. It is relational. So perhaps the universe is not expanding in the way we imagine. Perhaps nothing is moving outward. Perhaps the universe simply has a time-dependent geometry. That may sound like semantics, but semantics shape understanding. When we imagine stretching space, we picture a force. When we imagine evolving geometry, we picture structure. The difference is subtle but profound. The massive mistake may not be in the equations. It may be in our intuition. We mistook coordinates for physics. We mistook metaphor for mechanism. We turned a geometric feature into a material process. And in doing so, we made the universe feel more mechanical than it is. The truth may be quieter. The universe does not expand like a balloon. It does not tear itself apart. It does not inflate into emptiness. It simply exists as a space-time whose metric changes with time. That is less dramatic, but it is more precise. And precision is what physics demands. The next time you hear that the universe is expanding, remember, what we really mean is that the geometry describing distances between distant galaxies evolves. No cosmic wind, no rubber sheet, no explosion into nothingness, just curvature, just structure, just a space-time whose shape changes. The mistake was not in discovering expansion. The mistake was believing we fully understood what that word meant. And in physics, the difference between a metaphor and a mechanism can change everything.